Welcome back, AP Statistics. We are picking up with Chapter 12. This is the second section on observational and experimental studies, and we are deep into the weeds of an experimental study. So let's look at the 4 principles of experimental design. So just like dodgeball has 4 principles, if you've seen the movie, you know what those principles are, and we can debate whether there's 4 or 5. Experimental design has 4 principles too. The first principle is control. You control sources of variation other than the factors. Those are the explanatory variables that we are studying by making conditions as similar as possible for all groups in the study. So for example, in a study about the effectiveness of a brand of protein powder on the strength of weightlifters, all subjects should be eating and sleeping well so the data are not affected by those things. We want to limit outside influence from messing up our results. We want to show clear cause and effect between the protein powder in this example and the strength of weightlifters as it develops over time. We also want to randomize. This is no surprise that we're seeing randomization. We want to do that to equalize the effects of unknown or uncontrollable sources of variation. And mind you, we cannot eliminate uncontrollable sources of variation. I mean, that's just it. They're uncontrollable. We can equalize those sources of variation if we randomize effectively. We can't get rid of unknown variation, but we can disperse it with randomization. So for example, if there are 30 weightlifters, we can assign each weightlifter in the study a random number, directing 1 through 15 to refrain from protein powder and directing 16 through 30 to make a shake out of it each day before lifting. And here's the power of randomization. Suppose a few powerlifters dealt with illness during the experiment and we didn't know that. Even if we didn't know this, randomization spreads the uncontrollable source of variation, that is the sickness, between the groups. So if we randomize well using random numbers like we've described, someone criticizing our work cannot claim that illness would have completely messed up our results, since randomization spread those dealing with the illness between the 2 groups at random. All right, there are 2 more principles of experimental design we need to discuss. The first is replicating results, which we do in 2 ways. First, we involve a number of subjects and not just one. It's pretty obvious. A study involving one subject, so says our textbook, is an anecdote, not an experiment. It's just an account, all right? If we involve multiple subjects, that is a true experiment. It's pretty obvious. What's not as obvious is that one experiment, even if it's correctly done and yields a clear result, is not sufficient to really establish that result for researchers. We want to repeat the experiment with different participants or experimental units. So if one study yields a pretty obvious result, that is not the be-all and end-all. We want multiple studies that are saying the same thing, and then perhaps we can make a conclusion about whatever we're studying, whether it's something in the sciences or something in the social sciences or psychology or medicine or whatever. We want multiple studies. We want to replicate our results in that way, and each of those studies should have multiple participants because we don't want to be statistical dum-dums. And the 4th principle of experimental design, and this is one we only use if absolutely necessary, is blocking. And that is arranging participants or experimental units in groups that are similar to one another. This should remind us of stratifying when we were talking about sampling in Chapter 11, so that they can be dispersed evenly among the control and treatment groups. Now, what does that look like? This one's a little tougher to understand perhaps, but here's an example from the book. So for example, in a study on balance, if there are 10 participants and 4 are already gymnasts, for certain, we don't want them all in the control group or all in the treatment group. That would completely discredit our results. Perhaps it would be best to block for experience. That would mean that you randomize treatments that are administered to the group of gymnasts. So we randomly choose 2 for control and 2 for treatment out of the 4. And then separately to the group of non-gymnasts, we randomly assign 3 to control and 3 to treatment. That means that we have the same number of gymnasts and non-gymnasts in each group, control and treatment. So this would make experience a blocking variable that could assume 2 values, either you're a gymnast or you're not. So the levels of experience, gymnast and non-gymnast, are called blocks. And the process in total is called blocking. So blocking, we can see, is a compromise between control and randomization, right? Ideally, we want things to be as random as possible. However, we don't want, in this case, gymnasts or non-gymnasts being disproportionate in one of our groups and wrecking our findings. So blocking is a nice compromise between control and randomization. We randomize to an extent, but we don't get so randomized that we can't keep track of whether we have too many gymnasts in one group or another. Here's another example for blocking. In a study on whether music performance affects grades for senior high students, which would also be maniacal, just like our study from the past lesson on the effects of music performance on elementary students, where we forced some students to play music and forced other students not to play music. Perhaps students taking predominantly honors courses experience the effects of playing music differently than those who predominantly take academic courses. So what shall we do? We could make predominantly academic versus predominantly honors our blocking variable. Of course, that would assume 2 values, predominantly academic and predominantly honors. Those would be the levels of the blocking variable, right? So 2 obvious levels right there. You're either one or the other. And if we had 30 students and we knew 12 took primarily honors classes, we could administer treatment separately for the 12 honor students, split them between 6 control and 6 treatment randomly, and the 18 academic students, and we could randomly assign 9 to control and 9 to treatment. That would make sure the same number of honor students and academic students are split between the control and treatment groups. It's still random, but not entirely random, because we don't want honors or academic over or underrepresented in either the control or treatment groups. That is the power of blocking. Now let's apply the principles of experimental design we've discussed. We're planning an experiment to see whether the new pet food is safe for dogs to eat. We'll feed some of the animals the new food and others a food known to be safe, comparing their health after a period of time. This is, of course, the pet food study from our prior section. In this experiment, how will you implement the principles of control, randomization, and replication? Blocking is probably not necessary in this case. Give it a thought, see how you would control, randomize, and replicate, and compare your answers with the ones from our textbook. Okay, I'll assume we're ready to continue. If you need some more time, pause that video, but let's go on with the answers. So, first, we're going to control. You could control the portion sizes eaten by the dogs. To reduce possible variability, that's what control is for. We want to reduce needless variability. So to reduce possible variability from factors other than food, I would standardize other aspects of their environments, okay? Housing of the dogs in similar pens, ensuring each got the same amount of water, exercise, play, sleep time, for example. You want to make sure that the lives of these dogs are as the same as possible in every category other than the food they are eating. And I might restrict the experiment even to a single breed of dog and to adult dogs rather than puppies to further minimize the variation. So there are a lot of ways that we can control. We can minimize the amount of noise that we don't want muddying our results. Next, we're going to talk about randomizing to equalize traits, pre-existing conditions, and other unknown influences, basically things we can't control, things that we can't deal with up here. I would assign dogs to 2 feed treatments randomly. All right. So we would assign dogs randomly. Half the dogs would go to eat the food that we're trying to learn about, and the other would go to the safe dog food that was either known to be safe or apparently made in the kitchen of one of these textbook writers who thinks that they are all that when it comes to making dog food. And the last thing that we want to do is replicate. I would replicate by assigning more than one dog to each treatment, that's a no-brainer, to allow for variability among individual dogs. If I had the time and funding, I might replicate the entire experiment using, for example, a different breed of dog. We want to replicate our results by using multiple subjects, of course, and ideally we would produce results using different samples and see if they agree. If they do, perhaps we have established something. And if they don't, we have caught ourselves from making assumptions we should not make. And that is the power of applying the principles of experimental design, at least three of them.